So hello children, this is a sample paper of class 12 from Mumbai region. So let us see and try to solve it. Mumbai region, class 12, sample paper. So question is, extrinsic semiconductor is obtained by adding phosphorus atom to the silicon crystal. We'll have to draw energy level diagram. This is first question. And we have to name the majority charge carriers and what is the net charge on it. So 3 questions have been asked. So what is being done? Phosphorus is being added to silicon crystal. Okay, phosphorus is what type of atom? Pentavalent. It's a pentavalent impurity atom. So we know pentavalent means how many electrons does it have in valence shell? 5 electrons in valence shell. So out of these 5, 4 will be utilized in forming 4 covalent bonds. 4 covalent bonds with other silicon atoms. Right? 5th electron remains free. So 5th electron remains free. So 5th electron is remaining free. It means electrons are majority charge carriers. So you don't have to write this much. So your answer is, when pentavalent impurity is added to silicon crystal, electrons are majority charge carriers. So what is the answer to this part of the question? Electrons. Electrons are majority charge carriers. And what is the net charge? Net charge would be 0. Net charge on the extrinsic semiconductor would be 0. Even if you are doping with trivalent or pentavalent, after doping you have to remember that net charge would be 0. Right? Okay, majority charge carriers would be electron and net charge is 0. This is okay. Now let us come to the energy level diagram. So because electrons are majority charge carriers, so which type of semiconductor is obtained? N type. So you can see N type. So we will write this is N type. Who are the majority charge carrier? Electrons. Okay, now look and listen. Electrons are majority charge carrier. These electrons would be repelled by the other electrons present in the crystal. They'll be repelled. Repelled means due to repulsion what happens? Energy increases. Energy is more. Electron is being repelled, energy is more. So this electron is ready to be get lost, to be donated. So this is called donor energy level or donor atom. So energy is more. So see, what are the important points? Electrons are majority charge carriers, energy is more, and donor energy level. So energy more is here. This is energy more. This line is representing donor energy line. And it is just below the conduction band. These are 2 bands. This is conduction band, upper one. And the lower one is valence band. So you have to label these 2. And this line is important, this dotted line. This is donor energy level. Okay, because the electrons are majority charge carrier, they are being repelled, so their energy is more, and the energy is called donor energy level. So you have to mark like this. And you can see certain dotted, these black dots, these are electrons, which is in conduction band also, which is in valence band also. Okay, and this is hole. Hole will only be shown in lower band, that is valence band. It should not be, must not be shown in conduction band. So hole is to be shown here. Electron can be shown in both the sides, both the bands, and a number of electrons must be greater than number of holes. That is why electrons are majority charge carriers, and that is why it is N-type semiconductor. So this is an energy diagram for N-type semiconductor as well as for this question when phosphorus is being added to silicon. So you can prepare this diagram, and there is one more diagram. You can draw this as well, this N-type. So energy band diagram can be drawn by one way, which is shown up, and by the second way, which is here, this one. Conduction band, valence band. Okay, these are holes. So you have to write here, these are holes. Okay, these are electrons. Electrons are not shown separately here, because here they have drawn these lines. These lines are also representing the electrons are here. So dots, black dots, these blue dots are not shown both the sides, so that's okay. That is one way of drawing the diagram. So you can learn either this, but what is important, this dotted line is important to mark, to show that it is n-type semiconductor. This dotted line which is representing donor energy level is important. So this is how we can score full marks in this particular question. Let us move to the next. So let us see this question. It is explain formation of PN junction. Second question is this, hence define depletion region. So see, what is PN junction basically? These two I will show later. So whenever you take a silicon crystal, pure silicon crystal, pure semiconductor crystal. So what is this representing? It is a pure semiconductor crystal. You can write silicon crystal also. Okay, whenever we take a pure semiconductor crystal, and when we dope it, when we add to it, one side of it, when we add trivalent impurities, and other side we add pentavalent impurities. So you know, wherever you have added pentavalent impurities, that side will be rich in electrons. So it is called N side, or you can say N type. This is N side. This is rich in electrons because we have added this half with pentavalent impurities. And other side will become rich in holes. Trivalent means lack of electron, seat of electron, vacancy of electron, that is holes. So this becomes your P side, or you can say P type. So both the sides are separated by a fine line, and that line is called PN junction. This is PN junction. Now, because it can be connected to the circuit from two sides, this is called a PN junction diode. So why do we call it diode? Because it can be connected to the external circuit from two terminals. So, for example, they are asking what is a, like, explain the formation of PN junction diode. So you told it. When I was drawing it, when I was doing something, I was speaking something, and that is what needs to be written in the topic. So what needs to be written? That take a semiconductor crystal and dope one half with pentavalent impurities, other half with trivalent impurities. The side that you are doping with pentavalent will become rich in electrons. That is, it becomes N type semiconductor, and the other half where you have doped with trivalent impurity become rich in holes. So that becomes P type, and there exists a fine line, fine boundary which separates P region from N region, and this is called PN junction. This is how you can explain the formation of PN junction. Okay, then we come to potential barrier. They have asked about depletion region or potential barrier. Let us see. So they have asked about depletion region. So how do we explain that? So let us talk about the formation of depletion region. We'll talk about formation of depletion region. So the same story that we have spoken so far, that when we take a semiconductor crystal, this is semiconductor crystal, okay, and when we dope its one half with pentavalent impurities, okay, that becomes rich in electron, and that is your N side. Again, I am saying the same thing because the story, the concept begins with this only. And the other half you are doping with trivalent, right? So here holes are the majority charge carriers, and this line is PN junction. Now what will happen? Electrons will move from N side, this is P side, from N side to P side, from a region where they are more to a region where they are less. Electrons would move, so you will have to write, electrons start moving where to where? From N to P, okay, where their majority to a region where there binarity. Okay, from the region of higher concentration to a region of less concentration. Okay, so electrons are moving from N region to P region. So when electron moves, when this electron has gone there, what is left behind is positively charged donor ion. Okay, so you have to draw this diagram once more. Let us do that. So the electron has moved to this side, this electron. Right, so what is left behind here is positively charged donor ion. Okay, so similarly when hole moves from P to N, okay, this hole is moving from P to N, so it will leave behind negatively charged acceptor ion. Similarly, electron will move to that side once again and it will leave positively charged donor ion. And it will leave negatively charged acceptor ion. When electron moves, positively charged donor ion, so there is created a region. This region where this particular region, where what do we have? Where we have only, you can say fixed or you can say immovable. Fixed or immovable ions. Which ions? This is N side, this is P side. Which ions? You can say positive donor ion in N side near the junction. Right, this is N side near the junction. And what about this negative? This negative, what do you call as? Negative acceptor ion. And where is it? In P side near the junction. So this region where you have only fixed ions is called depletion region. Is depletion region, and that is how you can explain it. So what is depletion region? It's a region which is formed on both sides of junction. This line is junction. So it is formed this particular region on both sides of junction where what do you have? Only fixed ions. Which ion on which side you have to tell? Positive donor ion on N side near the junction. This has to be written complete, near the junction. And similarly, this side what do you have? Negative acceptor ion on P side near the junction. Near the junction must to be written. So let us get to the next question. Let us see question number 3. Two photons. What are photons? Packets of lights of wavelength 4000 angstrom and 8000 angstrom. So there are two photons of light. First wavelength is given as 4000 angstrom. Now angstrom can be converted as 10 into 10 to the power minus 10 meters. So this is my first wavelength. My second wavelength is of light is of photon is 8000 angstrom. Similar manner you can convert it into meters by multiplying with 10 to the power minus 10. Now our incident, so these two photons have been thrown on a metal surface of work function is this. So what is the value of work function which we can denote by phi naught if you wish, or you can even denote it by this W naught 2.5. And if you wish you can convert into joules, or let us see. So these two have been incident. This is one light, this is second light. Which of these two photons can cause emission of photoelectrons? So we know the condition. Condition for emission of photoelectrons. What is the condition for emission of photoelectrons? You can say, what is the condition for photoelectric effect? So the energy of the incident ray incident photon, energy of the incident photon must be greater than work function. It has to be greater or at least equal to. Greater or equal to. Okay, so you will find out the energy in both the cases. Let us find out the energy in both the cases. So energy will be equal to h nu 1. How to open nu 1? H, that is Planck's constant, C by lambda 1. What is the value of Planck's constant? You should know it. 6.6 into 10 to the power minus 34. This is the value of Planck's constant. I have opened it as this. C is speed of light, which can be written as 3 into 10 to the power 8. And what is lambda 1? Lambda 1 is 4000 into 10 to the power minus 10. I have substituted all the things, children, and you will get energy, but this energy will come in joules. You have to convert it into electron volt by putting like this term in division, that is an electronic charge. We have to put it in division. Then only we'll get the value in electron volt. So let us do this. So we can see it will be 6.6 into 3 upon 4000 into 1.6. All 10 power I am collecting here. So this is minus 34. This is plus 8. Then this will go up plus 10. This will go up plus 19. So let's see this. Minus 34 plus 8 is minus 26. Minus 26 plus 10 is minus 16 and minus 16. And this is plus 3. So basically we are left with 6.6 into 3 into 10 to the power 3 and 4000 into 1.6. So this 3 and this 3 is cancelled. So you can solve it and find out. It will come as 3.09 electron volt. So this is the energy of first radiation, right? So children, what have I done? I have done nothing. It's like h nu 1. Nu 1 is opened as C by lambda 1. Lambda 1 was given. I have substituted here. C I have substituted. H I have substituted. And you can put this term in division. You will get an electron volt. Okay. Now you have to similarly calculate energy of second photon. If they both are greater than the work function, which is given as 2.5, then photoelectric emission will be caused in both. If it is greater only in one case, then it will be caused in one case that you see. So let us get to the next. Let us see this question, question number 4 of the sample paper. An alpha particle and a proton. So I will write alpha particle this side. And I will write proton this side. This is how I do. Alpha particle symbol should be known to me. And proton symbol is 1h1. This is what I do in the beginning itself. For example, I will write charge of alpha particle is 2e. And here charge of proton I write by seeing this. This is 1. So I would write it is 1e. Mass of alpha particle will be this 4. 4 times mp. Similarly, mass of proton will be, this is 1. So this is 1 time mp, mass of proton. So you can see I just read alpha particle and proton and I could write this much. Okay, are accelerated from rest by same potential. So potential on both the sides is same. So potential on alpha is same as potential on proton. Capital V, it's not velocity, it's potential. Find the ratio of de Broglie wavelength. So we have to find out the ratio of de Broglie wavelength. So if you remember the formula, you can directly use it. Lambda is, this is a general formula again, h by root 2mq capital V, which is potential. Okay, this is general formula of de Broglie wavelength. So we can write it for alpha. When you are writing it for alpha, just write h and root 2 as it is, mass alpha, q, alpha and v. Similarly, you can write it for proton. which is H divided by root 2 mass proton, Q proton and V. Now you can divide. So when you will divide, you can see the quantities which are same will be cancelled. Right, this is how you can divide lambda alpha by lambda proton. So this can be written as H by this thing as it is. This I have written as it is. And here I will invert. This will go up root 2 m p q p v and divided by H. Now H and H are cancelled, like whichever quantities are similar you please cancel and don't show in the next step. For example, this you will not show, 2 you will not show, V you will not show because V was same. So we can write it as wavelength of alpha to wavelength of proton is equal to root has to be written mass of proton, ठीक है, mass Q of proton, mass of alpha, Q of alpha. So this is again in square root. Mass of proton, when you will see it's MP only. Q proton is E. Mass alpha is 4 MP and Q alpha is 2E. All the quantities you can see here when I wrote just from the symbol. This is a symbol of alpha particle. This is charge. This is mass. This is how we write. So when it's done, you can cancel out MP, MP and E. So what are we left with? Lambda alpha by lambda proton is equal to root MP cancelled, E cancelled. So what are we left with? 1 by root 8, that is 1 by 2 root 2. So this is the ratio of de Broglie wavelengths which is asked in the question. Let us get to the next question. Let's see section B, question number 4. Okay, so before this that was OR question. That was optional question. Okay, before this also I've spoken fourth question, but that was third question OR part. So this is fourth. What do you mean by transverse nature of electromagnetic wave? So what do we mean by transverse nature? Transverse, I remember like this and then I note this. Okay, so in transverse nature, we mean that the vibration oscillations are taking place perpendicular to the direction of propagation of wave. This is direction of propagation of wave. Direction of propagation of wave. Propagation means where the wave is heading to. And oscillations are taking place perpendicular to it. Okay. So what do we mean by transverse nature? That the oscillations are taking place perpendicular to the propagation of wave. So how do we show that? You know, in electromagnetic wave, particularly electric field and magnetic field both are oscillating because it's electromagnetic wave. Okay, so one is direction of wave, one is electric field, one is magnetic field. So if the wave is heading towards, suppose this is X. So electric field will be oscillating along this y-axis perpendicular to X. So you can show this way. This is electric field oscillation. And then magnetic field oscillation is shown along an axis which is again perpendicular to E and wave, yani ki X and Y. So that is along Z. This is magnetic oscillations. Okay, so just electric field and magnetic field, they both must oscillate perpendicular to each other and perpendicular to wave motion, wave propagation. So children, you can see, you can draw it this way also. See, this black is showing the direction of propagation of wave. This is electric fields oscillation, this is magnetic field oscillation. So this diagram is good enough. So this you have to label direction of wave motion, right? Red is showing electric fields oscillation. This blue, which is along z-axis, is showing magnetic fields oscillation. So that is how we justify the transverse nature of electromagnetic wave. What else they have asked? They have asked arrange the following electromagnetic waves in the order of their increasing wavelength: X-rays, radio and infrared rays. So this is how I remember. Rami Vux Y. That is how I remember. So, but this is frequency order. For me, it is frequency increasing order, right? Radio, micro, infra, then your visible, ultra, X, and this is gamma rays. Okay, Rami Vux Y. So this is for frequency. They are asking in order of wavelength, and which three they are asking? They are asking X, and then radio, and then they are asking your infra. These three you have to arrange in order of increasing wavelength. Let us go through the question once again. You have to arrange these three in the order of increasing wavelength: X, radio and infra. Okay, so let us see this. So this is frequencies increasing order. So this is wavelengths increasing order, opposite to that. So maximum wavelength is of radio. So radio will stand here. Radio's wavelength is highest. Then you can see who's coming. When we go like this, X is coming first and then infra. So infra is having higher than X. So X-ray would have least out of these three, and infra would stand here in between. So this is the order, and they have asked one application of each. So one application again, this in locating the fracture in the bones, X-rays, infrared rays in heating up the materials, and greenhouse effect, or any other technology like in remote and all, infrared sensing and all, and then radio in television and broadcasting, television and communication. So one application of each. Okay. So let us see the next question. So let us see question number 5. Sketch the path of refracted rays for red, green and blue when passed through a prism in the following diagram. If the refractive index of the prism for red, green and blue are these values. So find refractive index for red, refractive index for green, refractive index for blue. You can note down from the question itself. These are these. And diagram is this. And basically this is your right angled isosceles prism. It's given. Right angled and isosceles prism. So now children, we need to look at it using total internal reflection. You know, when will light not go out? Whenever angle of incidence is greater than critical angle. For light not to go out, or to suffer TIR, both mean the same. Total internal reflection means you are not going out. So when will light ray not go out? Whenever your angle of incidence is greater than critical angle. So I will take sine on both sides. So sine of I is greater than sine of IC. Now everyone knows that mu is equal to 1 upon sine IC. Okay, so sine IC can be written as sine IC can be written as 1 by mu. So let's put here sine I is greater than 1 upon mu. Let's invert it. So it will change. Sine I will be less than mu because I've reciprocated it. So it will change. Inequality will change. Now what is the value of phi? Because this is an isosceles prism. So for example, I am elongating this red. So it is 45 degree. I'll draw normal here. This is 45 degree. 45 degree. So I is 45. So I'll substitute here. Sine 45 is less than mu. Now sine 45 is 1 by root 2. 1 by root 2 is less than mu. Now what is the value of see, we can rationalize it. ठीक है, we are rationalizing it. तो ये कितना गया, √2/2. So it's 1.414/2. That is 0.707. So mu should be less than this, and then light will not go out. For light not to go out, mu should be greater than this. Sorry children, somewhere we did the mistake. So let's see these 1-2 steps back. Okay, see, I'll tell you where the mistake was committed. In just reciprocating the inequality. So let's see this. Rest everything is fine. See here, when I'm reciprocating it, this sin IC was written as 1/mu, that was okay. Now this will be inverted, that is also okay. Here I forgot to reciprocate. It is 1/sin I. Okay, so that was a small mistake. Now I'll put angle of incidence as 45. So let us put, so it is 1/sin 45. So 1/sin 45 is 1/√2. So that was a little mistake that was coming earlier. This will go up. So mu has to be greater than √2. And what is the value of √2? That everyone knows, it's 1.414. So wherever mu is greater than this value, light will not go out. Light will not go out if mu is greater than 1.414. Shall we see for which light is it greater than that? So it's greater here. So that means blue will not go out. And let us look at the value of mu once again. So it's this is 1.414. Mu is greater than 1.414. So who are more than 1.414? This is one value and this is also more. 1.44 is more than 1.414. So these two will not go out. This can go out. So you have to trace the paths. Okay, so you have to draw this diagram once again. So what have we found? Let us draw those three rays once again. Red, green and blue. And what did we find? That these two values are more. Blue's value is more and green's value is more. Only red's value is less. So red will come out, rest will not. So you can see red would go up to here and would come out. Dense center of error away from the normal. And green is not allowed to come from here, so it would go like this. Similarly, blue is not allowed to go from here, so it will go like this. So this is the ray diagram. This is the path of the rays. Important question. Again, to not to go out, you will not go out if your mu is greater than this value. So two rays were there whose mu was greater than this value, so they didn't go out from this door, from this transparent face. Okay, and they were reflected back. Right? Only this could go out. So let's see the next question, which is what is interference of light? This is one part of the question. And write the condition for constructive and destructive interference in terms of phase difference. So this is a 3 marks question. So first, coming to the interference that we know, when two light waves, you can form complete statements on your own. When two light waves, okay, of same frequency, mind it, same frequency, and having zero or constant phase difference. Either the phase difference is constant or it is 0. This is for phase difference. And what is one more condition? They are traveling in same direction. They should travel in same direction. So when two light waves of same frequency and 0 or constant phase difference traveling in same direction, when they meet, when they superpose, when they overlap, when they superpose, then their net light, net brightness gets redistributed. When two light waves of same frequency and traveling in same direction with 0 or constant phase difference, when they superpose, then their net light gets redistributed and somewhere it becomes bright and somewhere dark. Sorry, I should draw here. Dark and then again bright, then dark, then bright. So this phenomenon is called interference. So how would you define? When two light waves of same frequency and 0 or constant phase difference superpose traveling in same direction, then their net light, net brightness, net illumination gets redistributed in form of bright and dark fringes. This is called interference. Now we have to write the condition for constructive and destructive interference. Condition. So children, if condition come only for 3 marks, if conditions for constructive and destructive interference, then constructive interference, suppose first, then I would suggest you to go for the complete derivation if it is coming for 3 marks directly. But here, because definition is also asked, so you can directly answer it using the formula of interference, otherwise you should derive. Safe side, I would suggest to derive it, but otherwise you can just use this formula in brief. This is a formula of net intensity, and net intensity which is produced by the superposition of two waves. This is the intensity of first light, this is the intensity of second light, which were traveling in. See, the same definition is here. First light wave, second light wave, moving with constant phase difference in same direction, same frequency, they superpose, and this is the net intensity. Here, the constructive and destructive interference depends upon this term, cos phi. This term is called interference term. So this is your interference term. So you just need to talk about this in brief. But if it is coming only for 3 marks, like a single question, you should derive. So for intensity to be maximum, that is for constructive interference, it should be 1. Cos phi should be 1. For constructive, for bright fringes, it should be 1. So that means phi should be 0. Right. And after 2 pi, then after add 2 pi, then again add 2 pi, and so on. This is your phase difference, and this is what they have asked the answer in. So what is the last value, or you can say general value, that will be 2n pi. Okay, and n is starting from 0. So your phase difference, constructive interference, general formula would be 2n pi. N is starting from 0. Okay, but if it is asked for path difference, then you should know how to calculate path difference. Path difference is always equal to lambda by 2 pi into phase difference. In this question, they haven't asked, but they may ask. So you have to just substitute the value of this phi here. So path difference in that case would be lambda by 2 pi. It's 2n pi. So 2 pi cancelled. It will be n lambda, which is not asked. They have asked about phase difference. So let us do destructive के लिए. For destructive, For destructive interference, again you have to, for destructive interference, you have to talk about cos phi. So cos phi should be minimum -1. -1 comes for the first time at pi, then add 2 pi. Again add 2 pi and so on. So the last value would be 2n minus 1 pi. N is starting from 1. So this is the condition for destructive interference. To find out part difference, which they have not asked here. So you can put part difference is equal to lambda by 2 pi into phase difference, which is this last value. Pi would be cancelled and your answer would be ready for part difference. But right now they have only asked about phase difference. So let's see the next question. Let us discuss this question. What is diffraction of light? So diffraction you can say or diffraction you can say. So what is this? This is bending of light. But if you will write only bending of light, then it will be considered wrong. Bending of light around the corners of small obstacles. Around the corners of small obstacles or apertures. Okay, and it's spreading in the region of geometrical shadow. But where shadow is supposed to be obtained, if light is entering in that region also, that sort of bending is called diffraction. And it's spreading in the region of its geometrical shadow. Then to just explain diffraction, you can draw a small diagram as well. For example, this is a small aperture. This is a cardboard and small hole you can see. Source of light is here. So basically light should be obtained this way only. है ना? But what is the reality? That light is up to this. So it means light is entering in the region of geometrical shadow. Here shadow should be found, but here also light is entering. So that is diffraction. Okay, so you can just draw one diagram to show diffraction. So this is okay. We can elaborate like this. Now coming to the next part of the question, you will have to show the angular width of central maxima in diffraction pattern is twice that of secondary maxima angular width. So let us see how to answer it. Again, if I will answer it, I will go for the whole derivation, but it's okay. I'm telling in brief also. So for that, you have to remember what is the angular position of nth dark, that is nth minima in diffraction. So let us see what am I going to write. Angular position or angular width. You can say it both. Angular position of nth dark that is minima in diffraction. So you have to remember the formula. Notation is theta, angular width or angular position. Nth I am asking, so n I will write. So what is the general formula? It's simple. Is n lambda by d also some people write and a also. So it's a. A is slit width. This opening. Slit width is a. So this is nth dark minima. So how is it useful? So let us see. Whereas first dark minima obtained, I am putting 1. So it will be 1 lambda by A. So you can see this is my first dark. My first minima is obtained here. So now children, you can see this is my central maxima, and here is my first dark, and this side is also my first dark. So because I've got the value, let me label it. Just see this value and label it. This is lambda by A and this is minus lambda by A because first dark is obtained this way. Okay, so what is the width of central maxima? This much, right? So what is the width of central maxima? Please write down width of central maxima. Subtract the position upper reading minus lower reading. So lambda by A minus lambda by A. Correct. So what it is? 2 lambda by A minus will be plus and it will be 2 lambda by A. So this is the width of central maxima. Width of central maxima which we have found as this. Fine. Now come to again one more formula. Whose formula? Angular position also you can say. Width also you can say. Of whom? Nth maxima. Right. Nth maxima. So what is the formula? You have to remember it. Theta n for bright we are writing. So what is the formula? It's 2n plus 1. 2n plus 1 lambda by 2. And n is starting with 1. So let us put 1. So theta 1. My first I am obtaining. So it's theta 1. So or you can say theta 1 I am putting here. Let it be 2 into 1 is 2 and plus 1 is 3. 3 lambda by 2. This is my first maxima. So where is my second maxima? Now I wish to put n is equal to 2. Substitute here n is equal to 2. My second maxima is obtained at 5 lambda by 2. So what is the this fringe width? Directly also you can use fringe width is also lambda d by A. Okay children, so I went till fringe width which is not required here. What was required is this much only. This angular width of central maxima is this much. What is the general fringe width? Fringe width is lambda d by, some people use small d, they can use small d, I am using A. This is fringe width, general. So what is the angular width? Angular width, just don't write this capital D. So this is lambda by A. So you can say width of central maxima is double of this. That is the question. Let us see this once again. It's important. See, what did I start with? Its angular position. Whose angular position? Nth dark. Angular means theta, nth is n, and what is the formula? N lambda by A. A is slit width. So where is your first dark? N is 1. So put n is equal to 1. This is my first dark. Then I get to this diagram. Central is here, first dark is here, both sides are central. So this is lambda by A because I obtained, and then this side also minus lambda by A. Then I subtracted upper value minus lower value, I got the width. Then you talk about fringe width. Fringe width general formula is this. And when you don't write this capital D, it becomes angular width. So you can see width of central maxima is double of angular width of any bright or dark, doesn't matter. It is double. So this is how you can prove it. Okay. So let us get to the next. Let us see the next question. In next question, in Young's double slit experiment using red light of wavelength this okay, fringe width obtained is this. So what is the fringe width obtained? 2.66 into 10 to the power minus 3 millimeter. Okay, and what is the light you have used? It's 8000 angstrom. So when you use 8000 angstrom, you are getting this as fringe width. Now the question is, what would be the fringe width? Okay, what would be beta 1 when red light is replaced by violet light of 4000 angstrom? So you can say, CK, wavelength is half, and 4000 angstrom is half of 8000. So new wavelength is half of old wavelength. So what is the formula of fringe width? Fringe width's general formula is lambda d by d. So you can say when wavelength would be half, fringe width would be half. It is directly proportional. So when wavelength would be half, fringe width would be half. So whatever is the fringe width mentioned in the question, that would be half. So new fringe width would be 1.33, half of this into 10 to the power minus 3 millimeter. That is the answer. Second, complete interferometer setup is immersed in water of refractive index this. So again, let us see what is given as fringe width, 2.66 into 10 to the power minus 3. View it as an independent question, and wavelength has been given as 8000 angstrom. Now they are saying the entire setup is immersed in water. So we know that the new fringe width would be, whenever you are changing the medium, it will be 1 by mu times of original fringe width. New fringe width will be 1 by mu times original fringe width, which is given this. And mu is also given to you, it's 1.33. So just substitute mu here and beta here, you'll get the answer. The next question is, distance between sources is reduced by half and between source and screen is doubled. So basically this is slits. This is written wrong here. It will be slits. So distance between slits is half and source and screen is doubled. So let us get to it once again. Beta's general formula is lambda d by d. So this d is half, okay, and this d is doubled. So new and new and new fringe width. So lambda is lambda, this d is this double, and this is half, so d by 2, it will go up. So it is 4 times lambda d by d. So you can say it will become 4 times. Fringe width will become 4 times original value is given. So this can be solved. So children, I have discussed 7 questions here. So 5 questions are left that I will cover in next video. And I'd be again presenting some sample papers of various regions, and whichever sample papers of class 12 are available to me, I would try to solve and post here in the upcoming days. And if you have certain doubts, like if you want me to solve a particular topic, teach a particular topic or certain numerical problem, then you can share to my mail ID. You can mail me the problem, and hopefully as and when I get time, I would be solving and posting it here. So thank you.